Picture August 27, 1939. A stubby jet prototype rises without a propeller, only a raw metallic howl. From basement experiments to engines that swallow cities of air each minute, how did we teach fire to fly? In this series opener, we'll trace jet engines from bench rigs to today's geared giants and open-fan dreams, meeting the minds behind them and the moments that changed everything. So you can guess what's coming next. In the late 1920s, a young Royal Air Force cadet named Frank Whittle sketched a radical idea. Forget propellers. Compress air, ignite fuel, spin a turbine to power the compressor, and let the hot stream push the aircraft forward. He filed his patent in 1930, and by 1937, his compact centrifugal turbojet roared on a test stand. Whittle wasn't a corporate titan. He was an obsessed problem solver, scraping resources to found power jets and prove that a continuous, high-speed airflow could do what pistons and props could not. His personal arc, working-class roots, dogged persistence, and a thesis dismissed as fanciful, gives the technology a human heartbeat. He wasn't just inventing hardware, he was inventing confidence that flight could outrun its old limits. Meanwhile, in Germany, physicist Hans von Ohain pursued the same dream from a different angle. Backed by industrialist Ernst Heinkel, he refined a clean annular combustor and experimented with hydrogen to tame early combustion instability. On August 27, 1939, his HS-3B powered the Heinkel HE-178 into the history books, the first jet flight. Where Whittle's centrifugal compressor prized simplicity and ruggedness, Ohain's work foreshadowed sleek axial designs. Two young minds, two paths, one breakthrough. Jets had arrived. The jet engine's roots are older than flight. In 1791, John Barber outlined a gas turbine concept: compressor, combustor, turbine. But metallurgy and sealing couldn't deliver the needed pressures or temperatures. In 1903, Egidus Elling finally produced net power from a small gas turbine using a centrifugal compressor, proving the thermodynamic loop could work. These were seeds, not airplanes, but they framed the cycle every modern jet still follows: compress, burn, expand. Then manage heat and losses well enough to make useful thrust. The first practical aircraft turbojets emerged in parallel. In Britain, Frank Whittle championed a compact centrifugal compressor that could be built with the machine tools of the day. In Germany, Hans von Ohain leaned toward cleaner aerodynamics and an annular combustor. Whittle's engine ran on a stand in 1937. Ohain's OS-3B flew in 1939 on the Heinkel HE-178. Both solved the same puzzle: keep air flowing smoothly through a compressor, add fuel without blowing out the flame, extract enough turbine power to sustain the compressor, and leave a high-velocity exhaust to push the aircraft forward. War accelerated everything and exposed limits. The German Jumo 004, an axial flow turbojet, powered the Me-262 to unprecedented speeds, while Britain's Gloucester Meteor introduced jet operations to the RAF. Yet, early alloys and primitive blade cooling meant short service lives and frequent overhauls. The lesson stuck. Aerodynamic ideas succeed only when materials, cooling, and manufacturing keep pace. That insight, more than any single blueprint, set the trajectory for the next 80 years. After the war, turbojets matured for speed, but airliners needed range and economy. Enter the turbofan. By routing a large cold stream of air around the hot core, turbofans traded raw jet velocity for propulsive efficiency at subsonic cruise. Rolls-Royce's Conway proved the concept in service. Boeing's early jets soon migrated from thirsty turbojets to mixed flow and then high bypass turbofans. The change looks simple on paper, add a big fan up front, but it transformed fuel burn, noise, and the economics of global travel. The wide-body era amplified the idea. Pratt & Whitney's JT9D and GE's CF6 swung ever larger fans and higher bypass ratios, letting aircraft like the 747, DC-10, and A300 carry more people farther on less fuel. Higher overall pressure ratios in the core squeezed more work from each kilogram of air, while multi-stage compressors with smart variable stators kept the operating map stable across throttle settings. Fuel nozzles atomized better, combustors mixed cleaner, and turbines extracted power with fewer losses. Materials quietly became the star. Single-crystal superalloy blades resisted creep at searing temperatures. Internal serpentine passages and film cooling bled just enough air to shield metal surfaces. Thermal barrier coatings added precious degrees of margin. Each incremental step raised turbine inlet temperature and core pressure ratio, unlocking either more thrust or the same thrust at lower specific fuel consumption. Durability followed. Where early engines survived tens of hours, modern commercial turbofans routinely run thousands between shop visits. Big thrusts brought new structures. The GE90 family showcased carbon fiber composite fan blades and wide-chord aerodynamics that shed weight while maintaining strength. Larger fans also meant lower exhaust velocities and less community noise, a win for both neighbors and airlines. Serrated nozzle chevrons and acoustic liners further tamed the roar by mixing shear layers and absorbing tonal peaks, making high-bypass engines not just efficient, but civil. Digital brains sharpened analog muscles. Full-authority digital engine control, or FADEC, tuned fuel flow, variable geometry, and clearances in real time, protecting the engine while squeezing out performance in hot and high conditions. On-condition monitoring and big data analytics turned maintenance from reactive to predictive. Vibrations, temperatures, and pressure ratios became early whispers of wear, reducing unscheduled downtime and cost. Manufacturing leapt forward with composites and additive. 3D-printed fuel nozzles consolidated dozens of brazed parts into single pieces with fine internal passages, improving atomization and cutting weight. Ceramic matrix composites arrived in hot sections where metal once wilted, enabling higher temperatures with less cooling bleed. The cumulative impact is subtle but compounding. Every gram saved at the fan, every degree added at the turbine ripples through the cycle and the airframe. Architecture evolved again with gearing. Pratt & Whitney's geared turbofan places a reduction gearbox between the low-pressure turbine and the fan so each can spin at its happiest speed. Slow, quiet, and efficient for the fan, fast, compact, and effective for the turbine. The result is a fatter bypass stream, improved propulsive efficiency, and the platform poised to benefit from future materials and combustor gains. It's a mechanical tweak with strategic consequences, much like the first shift from turbojet to turbofan. Finally, fuel flexibility began moving from demonstration to deployment. Sustainable aviation fuels, drop-in blends refined from biomass, waste, or synthesized hydrocarbons, allow today's engines to cut life cycle emissions without redesign. They don't change how a turbofan works, but they change what flows through it. Meanwhile, ambitious experiments, open fan propulsors that revisit the prop fan promise with better acoustics, hybrid electric assists for regional routes, and even hydrogen combustion probe the edges of what a jet can be. Each builds on the same disciplined choreography refined since Whittle and O'Hain: compress, burn, expand, recover, and keep pushing losses down. Thread these milestones together and a pattern emerges. Progress in jet engines is less about singular eureka moments than about stacking compatible improvements. Fans that move more air gently, cores that run hotter and cleaner, brains that guard the hardware, and fuels that bend the carbon curve. The result is a machine that looks familiar from the outside, yet embodies generations of quiet revolutions inside.
One of aviation's strangest twists is that a British engine helped define an early Soviet icon. After the war, Rolls-Royce sold its Neen turbojet to the USSR for civil use. Within a heartbeat, it was reverse-engineered into the Klimov RD-45 VK-1 that powered the MiG-15. East-West politics aside, the episode shows how quickly jet know-how could leap borders and front lines. Another shock was how fragile the first combat jets really were. The Me-262's Jumo 004 brought axial flow brilliance to the skies, but with limited nickel and immature cooling, many engines lasted mere dozens of hours. Pilots had speed, mechanics had headaches. The lesson that stuck for generations: metallurgy and cooling tech can win or lose entire eras. America's jet chapter began with a quiet nudge. After seeing Whittle's work in Britain, U.S. General Hap Arnold rushed a crash program that produced the Bell P-59. It wasn't a world beater, but it trained pilots, seeded industry, and opened the door for the P-81 and the turbojet mainstream. Finally, the prop fan that almost changed airliners. In the 1980s, the GE-36's open rotors promised huge fuel savings, but stalled on noise and timing. Decades later, that DNA returns in modern open fan concepts, proof that ideas rarely die, they wait for better tools. The present is a stack of quiet revolutions. Geared turbofans let the fan loaf while the core sprints, squeezing more miles from every kilogram of fuel. Bigger, lighter fans, often with composite blades, push bypass ratios higher. Inside the hot end, ceramic matrix composites and intricate 3D printed fuel nozzles raise temperatures and finesse mixing, while FADEC plus digital twin analytics turn maintenance into prediction rather than surprise. The once shelved open fan is back with better tools. By placing a single large propulsor in the breeze, sometimes unshrouded, designers chase double-digit fuel burn cuts. The trade-offs are certification, blade dynamics, and community noise. But with smarter acoustics and variable pitch, it could land first on single aisles where savings compound fastest. Hybrid electric architectures are moving from whiteboards to flying test beds. Think megawatt-class electric machines assisting takeoff and climb, then idling while the gas turbine sips cruise fuel. The physics favors short-haul and regional routes, where battery mass and thermal management are tractable and quick turnarounds matter. Fuel is evolving too. Drop-in sustainable aviation fuels already work in today's engines, cutting life cycle carbon without redesign. Farther out, hydrogen promises zero carbon at the point of use, but demands cryogenic tanks, new airframes, and new airport plumbing. Defense brings its own frontier, adaptive cycle cores that can flow extra air for range one moment and switch to thrust the next. Different paths, same choreography. Compress, burn, expand, only cleaner, cooler, and smarter. In barely a human lifetime, the jet engine leapt from benchtop curiosities to city-bridging machines. Yet its heartbeat never changed. Compress, burn, expand, then do it smarter. Each era stacked a different strength on that rhythm. Whittle's and O'Hane's faith in continuous flow. Wartime lessons in materials and cooling. Civil aviation's pivot to propulsive efficiency. And today's marriage of composites, ceramics, and algorithms. The result is quieter cabins, longer ranges, and fuel bills that no longer dictate every route. Now the frontier shifts from how fast to how clean. Open fans promising double-digit savings, hybrids that lend a shove at takeoff, and fuels from SAF to hydrogen that reorder the carbon math. We solved speed. We're engineering stewardship. So here's the question to carry forward. Will the next big step arrive as a gear giant, a whispering open fan, a hydrogen flame, or an elegant hybrid we haven't named yet? And how will it change where and how we fly? If this journey through jet history clicked for you, tell me which era hit hardest. Whittle and O'Hane's first leaps, the turbofan revolution, or today's geared and open fan experiments? What evolution should we unpack next? Concorde versus modern twins, how 3D printed parts reshaped engines, or the real prospects of hydrogen? Drop your take below. I read everything. If you know someone who'd enjoy this story, feel free to pass it along. And if you like deep, human tech explainers, you'll probably enjoy the playlist waiting on the channel. Start with the locomotive episode or jump straight to turbines. See you there.